First, let me describe this problem. Knapsack problem. Okay, yeah, very interesting. Given n items of known weights W1, W2 through Wn, and the values corresponding to these n weights V1 through Vn, and a knapsack of capacity, capital W, capacity, okay, knapsack. So you want to carry some of the weights, okay, yeah. Find the most valuable subset of the items that fit into the knapsack. The constraint, you have a constraint. You cannot put all the items into it. Okay? You have to select subset of items, but you want to maximize the total value of that subset. Okay? So we need to solve the problem. Okay? All right. Assumption for convenience. So we do not change the difficulty, but we want to make our discussion a little easier. Yeah. All the weights and the knapsack capacity are positive integers. That's awesome. All these W's and capital W, all positive integers. But we do not need these V's, non-necessary integers. Okay, yeah. But in our later, when we use a concrete example, all the values are integers because that looks, clean, right? So we will feel better. We don't want to see 8.3579, very messy. We don't want to see that. Yeah. So in our example, we will use good numbers. All right. How to define subproblems. Dynamic programming, we need to define subproblems, then derive recurrence relation. Derive recurrence relation between a subproblem and the original problem. Size reduction. Look at the size reduction. Okay? And a single piece reduction. Think about that. Single piece reduction. Yeah. Could be useful. That idea could be useful. Okay? Yeah. All right, so let us define subproblems. Idea still reduce problem sizes from n to I, and I, some number between 1 and n. Okay? So for the general subproblem, we consider the first I items of n items. First I. Then we gradually increase that I number. At the beginning, I is 1. At the end, I equals n. So we solve the whole problem. Yeah. W1, W2, Wi. Okay. With values V1, Vi. Okay. Capacity number W equals an integer J. Another integer. So we use J. Here you can see there are two variables. Integer I, integer J. Two variables. So we need to define a function. Optimization function. Yeah. All right. Subproblem function with two variables. Parameters I and J. Okay. Function value f of ij. What's the meaning of that? Straightforward. The meaning, straightforward. The value in the knapsack that corresponds to an optimal solution. Yeah, the total value in that knapsack. But we want this value corresponds to the maximum value solution. That's it. That's the straightforward definition of our subproblem. So with this definition, next we need to derive recurrence relation. All right. Now, for this case, because our subproblem using general integer I, so now we want to consider two adjacent subproblems. Yeah, because when you do derive recurrence relation, there is a commonly used idea. So we consider two adjacent subproblems. Okay, yeah. What's the relationship between two adjacent subproblems? All right. So the basic idea, we increase I one by one. So every time we increase that I by one, that's why we get two adjacent subproblems. Okay. So we explore the relationship with the same capacity J. Yeah, same capacity J. So let's fix that J. Later we can change that J. We fix that J. Okay? Yeah. Next, let us consider the relationship between two other adjacent subproblems. Okay? So let me draw a diagram to explain the idea. Okay? Suppose, the line segment, the whole line segment corresponds to the capacity W. But when we consider subproblem, we do not use the whole capacity. We consider capacity J for one particular subproblem. And in this special case, we consider these weights from W1 through Wi. So the optimal solution for this case corresponds to f of ij. All right. Next, let's consider another subproblem. But for this subproblem, we reduce one weight. Okay? So we can call single piece reduction, or we can call two adjacent subproblem. Okay? So anyway, you can call it. All right. This case corresponds to this subproblem function. Yeah. The question is, what is the gap between these two subproblems? These two subproblems, the main difference we need, so here, there is a hidden condition. When we want to compare the difference, we may need to use this hidden condition. Okay, so what's that? Each weight is only used once. Each weight you can only use once. You cannot use more than once. No. One item, if you put in a knapsack, it's done. You do not have a second chance to put, two items with the same weight, right? Yeah. It's not that assumption. The assumption is, that's why it's hidden. Okay? Yeah. In the question, it's not explicitly stated in that way, but that's the meaning for the original knapsack problem. Okay? Then, our first decision, we need to determine if Wi is used or not. If the Wi is used, that corresponds to this case. If Wi is not used, that corresponds to this case. So we compare these two cases and see what is the difference. All right. Now, the recurrence relation part. Yeah. Okay. With Wi, what do we get? if we use WI, we can only use it once. After you use this WI, then you do not have a chance to use it again. That's why that hidden condition is very important. All right. So now we use it once. Use it right here. After we use it, the remaining capacity, there is a remaining capacity. Okay? Yeah. So we can only use WI through WI minus 1, but for the remaining capacity. Okay? Yeah. All right. The remaining capacity, this is the capacity number we updated, J minus WI. That's the remaining capacity. But we use the weights from item 1 through item I minus 1. So the optimal solution is this. Right? Yeah. So the total value for this case, VI, it comes from WI. Okay? Then remaining capacity, the best solution is this. So we add them together. That is the best we can get for this case. Okay? All right. So that is with WI. Without WI, that's easy. Without WI, that's this, right? That's this number. Okay? Then we combine these two cases. So we get this. Okay? Yeah. One choice like that. Another one. So you have this possibility, but this option may be better than that, right? Although you have a different option, you can use WI, but it is not guaranteed. If you use WI, you can get a better solution than without using WI, right? So you still need to compare these two cases for a better solution, with or without. Okay? Yeah. So that is the final recurrence relation. This one. Okay? Yeah. That's for WI less than equal to J. Because in this condition, this is greater or equal to 0. Otherwise, it's a negative number. The second term does not mean anything, right? Yeah. So for WI greater than J, you cannot use WI. So that's why we just consider this case. Yeah. Right. So now after we have the recurrence relation, the next question, how to implement it, how to use it to organize our data to solve the problem. That will be our part 8.5, the last part of this class. Okay, yeah, so we finish this part. Oh, okay.